Hello viewers, today I will introduce you to the history of microscope, different concepts which is used to understand the working of the microscope and the different types of microscope. It is very difficult to attribute the invention of microscope to any particular person. But the first reports came in 1595 when Dutch opticians and spectacle makers Jacharia and Hans Janssen first used a system of lenses, especially biconvex and plano-convex lenses using draw tubes where they doubly magnified the images. They also used it to see various other objects. Now, it was Robert Hooke, the British chemist as well as mathematician, who is attributed to the discovery of the first compound microscope. Now, Hooke used it to observe sections of plant tissue, and he also reported it in Micrographia, where he coined the term cells. The father of microscopy, who is Antony van Leeuwenhoek, who is a contemporary of Hooke, invented the better version of the compound microscope. Not only he did that, he utilized it to observe various microorganisms like bacteria, protists, even the RBCs, and his reports were sent to the Royal Society, and it actually became the foundation which made people at that time aware of the importance of microbes and helps in better understanding of the contributions of microbes in biology. The early 18th century also saw further improvement in the microscope. It was Charles Hall who first invented what we call the achromatic lenses, which actually helped microscopist or lens developer at that time to get rid of various defects in the lenses. This was patented by John Dollond in 1750s, and he actually was the first who further developed the technique of making lenses free of lens aberrations. Now, it was in 1830s when the Englishman Joseph Lister made a significant invention. He made lenses which actually solved the problem of spherical aberration. In 1866, it was Ernst Abbe, who was associated with the Zeiss optical work at that time, who gave different theories due to which the whole world of microscopy changed. It was Abbe who propounded that just increasing the magnification by lenses does not increase the information content in the images that are being captured or that were observed during that time. And he also developed certain condenser which was used to focus light from the source into the objective lenses. Then another significant discovery happened in 1893 when August Kohler, he was also a German associated with the Zeiss, he developed a technique so that light is focused in such a way and it reaches the specimen, it will cause even illumination of the specimen. And this was very important discovery at that time because there was uneven illumination in most of the microscope during that time. The next important discovery happened in 1930 by Fritz Zernike, who developed a technique to observe live organism without staining them, or even fixed organism but without staining. That is the foundation of what is nowadays called phase contrast microscopy, which actually came into use in 1942s, and due to this discovery, Fritz Zernike obtained Nobel Prize in 1953. In the 1950s, another important discovery happened, and that was by George Nomarski, and Nomarski actually suggested and devised what is now known as Nomarski interference contrast microscopy or differential interference contrast microscopy. These were very significant discoveries during that time. After the significant contribution in the electronic science, people integrated the systems of optics along with electronics, and then it was devised what we nowadays call the confocal microscopy. The prototype was made by Marvin Minsky in 1957, and later it came into commercial use in 1987. Now, the confocal microscope, unlike all the other microscope, is so very important because it can do optical sections. The optical sections are nothing but using the light coming from a pinhole to observe different regions of tissues at different depths. Now, coming to the aim of microscope, the major aim of optical microscope is to attain good magnification without compromising the resolution.
So, what is resolution?
The resolution in case of microscopy is defined as the ability of any lens of a microscope to distinguish as two close points as two distinct entities. So I will come to the details of how you distinguish it later on. Now I will introduce you to different parts of the optical microscope. In this case, a bright field microscope. Now, the first and the most important thing is the light source. Here we have a light source whose power can be adjusted with a screw here. Then the light coming from it reaches the condenser lenses, which is here, and the condenser lens has an iris or diaphragm which controls the amount of light which is coming to the specimen plane. So I can fiddle around with the iris. This is the stage where we place the specimen or the slide containing the specimen. This is a stage slide holder, and I can move the slide using this slide holder on the stage. Let me introduce you to the inscription on a particular lens. So let me take out the lens. Now you see that it is written 40x. 40x is the magnification of the lens, and then 0.65, which is the numerical aperture. Light from this lens now travels through this body tube and reaches the eyepiece, which is another set of lens having a magnification 10 in this case. Because this is a trinacular microscope, this is the port for the camera. This is the arm of the microscope which is attached to the base of the microscope. Moving to different concepts which is important for understanding the working of a microscope, let me first introduce you to the concepts of geometrical optics. Lenses form the most important part of optical microscope. Now if you take a look at the image, you will see that there's the lens and the principal axis. Then the object is present on one side of the principal axis and the image is formed on the other side. Now the lens I'm talking of is a thin lens. The distance between the principal axis of the lens and the object is known as the object distance, and that between the image and the principal axis is known as the image distance. So let's say if small b be the image distance and if small a be the object distance, then by the formula which you are observing, we get that the focal length, which is small f, then the relation between them is 1 by f is equal to 1 by a plus 1 by b. Now, another important concept while trying to understand the lens is magnification. So what is magnification? The magnification or the magnifying power is the ability of a lens to make the object as big. That is, the image of the objects now appear bigger in size without physically increasing the size of the object. And how is it related to the image distance and object distance? So if capital M be the magnifying power or the magnification, then capital M is equal to the size of the image by size of the object, which is equal to B by A, that is the image distance by the object distance. Is there any relation of this with the focus? Yes, even there's a relation m is equal to f by a minus f. Now coming to another concept, which is what are positive and negative lenses. This also depends on the capability of lens to focus a parallel beam of light. A positive lens is such a lens which can focus a parallel beam of light at a certain point. For example, a convex lens can act as a positive lens. A negative lens, as you can see in the figure, is such a lens which actually can diverge a parallel beam of light. A concave lens, which is both sides concave or biconcave, can do such an activity. Now, talking of magnification, I should mention here that just increasing the magnifying power of a lens will not increase the information content. And this was also what Ernst Abbe proposed. And whatever is the magnification then without increasing information is known as empty magnification. Now, how can we solve the problem of empty magnification? Before going into that detail, let me introduce you to two more terminologies in the concepts of microscopes. The first is the f number or the f-stop, and second, the numerical aperture of a lens. Now both the f number or the f-stop and the Na is attributed to the objective lenses. Now what is f-stop? F-stop is actually defined as the ratio of the focal length versus the d, which is the diameter of the lens. Now, if you increase the diameter of the lens, the f number goes down, and lower the f number, more light goes into the lens. Now, if you decrease the diameter of the lens, then the f number goes up. That means lenses having higher f number will have less light going into it or dimness in the image. This is most important for people working behind the camera. Now, in case of microscope, similar to this, we have also the numerical aperture. What do we mean by numerical aperture? The numerical aperture of a lens is defined as the cone of light, which is a solid cone of light, which enters the objective lens. And theoretically, it is Na, which is equal to small n into sine theta, where small n is known as the refractive index of a lens.
Sir, I have a question. I have seen people using air as the intervening medium for lenses. I have seen people using oil also. Sir, what is the advantage of using oil as the intervening medium for lenses?
Yeah, good question. So let's look at this image. So if you see that the importance of refractive index, oil has a refractive index more higher than that of air as an intervening medium. Now if you look at the image on the left hand side, you will see we have used air as the intervening media. Some of the rays coming from the specimen actually does not enter the object. However, if I use oil as an intervening medium, because of higher refractive index, most of the cone of light will now enter the objective. So what we does by using oil, we increase the amount of information by increasing the cone of light which enters the objective. Now, the brightness of the image is thus enhanced by decreasing the f number, and there is also a relation between the resolution which I have discussed previously of the microscope, and the numerical aperture. So what is this? If you look at the relation, if D is the distance between 2 points in the specimen which are close together, and if lambda is the wavelength of incident light and Na is a numerical aperture which is n sine theta, then we see that D is equal to 0.61 lambda by numerical aperture. So what I mean by this statement is that smaller the value of D, more is the resolving power of a lens. That is, we can see very small points which are present close together as distinct entities. So it varies with wavelength and it varies with the numerical aperture. If we consider the different lenses which is present in a compound microscope, then other than the objective, we have a condenser, and both have its own numerical aperture. So the ultimate resolution of that microscope will depend on the contributions by the condenser as well as the objective, and it can be shown by the formulae D is equal to 1.22 lambda by any of the condenser plus any of the objective. Theoretically, it is believed that the resolution of optical microscope is half the wavelength of incident light. Now, while we have get acquainted with various concepts in use of a microscope, we should now be also aware of various defects which happen while taking an image. Now, these are defects associated with the objective lens. Now, what are they? These are better known as lens aberration. But before going into the different types of lens aberration, let me also make you aware of the importance of knowing of this lens aberration. Now, once you capture an image or whatever your observation is, if you're not aware of lens aberration, you might take a distorted image as what the specimen itself is, and you could be very well mistaken. Now, coming to types of lens aberration, there are 4 different types. 2 of them are known as on-axis aberration and 2 of them off-axis aberrations. I am not going into the details of various other distortions which may also happen. Now, coming to on-axis aberration, the first can be chromatic aberration. So what is chromatic aberration? Chromatic aberration happens because the lens actually can focus different colors at different points. So the blue light is focused earlier in the optical axis, while red light is focused slightly away from the optical axis on a focal plane. That means in that image you will see a slight halo occurring around the focus.
Sir, how is this problem of chromatic aberration of lenses solved?
Yeah, the problem of chromatic aberration can be solved by using achromatic doublet lenses made up of crown and front glasses which focus all of these different color at the same point in the image plane. There is another type of on-axis aberration as you look into the figure that is known as spherical aberration. This is the lens focuses a parallel beam of light at different positions in the image plane from the central part and from the peripheral part. This can also be rectified by using proper negative and positive lenses, that is a combination of both, so that all the light which is coming from the central part as well as the periphery is focused at the same point in the image plane. Now again look into the figure, what we see that there are some off-axis aberration. They are coma and astigmatism. So what is coma? The coma results in the formation of a streak of light having somewhat similar to a comet tail. Now this is more profound if the rays hit the object obliquely. Astigmatism also results in the formation of short streaks at different focal point. The more the object is displaced away from the optical axis, more is coma and astigmatism. coming to the illumination of microscope, it is worth mentioning that there is two types of illumination. One, the critical illumination, and one, cohler illumination. One of the disadvantage of critical illumination is that the specimen is not evenly lit up. This was solved in 1893 by August Kohler, who suggested using a particular setup before the condenser lens just after the source of illumination, so that the image of the illumination, which can be a lamp, is actually obtained at the specimen plane and the specimen is evenly lit up. Now, if you look into the figure, what you will see that Kohler illumination requires a collector lens, a fill diaphragm, a condenser diaphragm, and the condenser lens. Now, the importance of all these things is that we obtain a condensed beam of light which is evenly spread, reaching the specimen, and hence even the image appears to be well and evenly lit up. Now, this brings us to the end of the section. Before we go into the discussion about different types of microscope, I should mention that in modern day, the objectives are made up of good glasses having high numerical aperture, and the objectives are also parfocal in nature. So what is parfocal? So parfocal is if you change the position of the objective, the specimen will not go out of focus. Coming to different types of microscope, I am talking of light microscope. They can be categorized based on their source of illumination. Now, they can be bright field microscope, dark field microscope. Regarding whether the source has coherent light and whether they are coming in phase or not, it can be phase contrast microscope, which is mostly used to observe unstained specimens. Then there is differential interference contrast microscope. Coming to bright field microscope, it has a source of illumination which can be the ambient light in your room or some artificial light. There may be some mirrors which focus it, and then there are objects or the specimen which is present on the slide in the object plane, and there you can lit up the object and then observe the image. Now, one of the important concepts of bright field microscopy is that you have to enhance the contrast of the object or the specimen with respect to the background in the immediate vicinity. And this can be done by staining with colored dyes which impart or enhance the contrast. Now, there are other types of microscopy, and before I go into it, it will be worth noting what are the things which can be imaged using bright field microscope. One, bacteria, other small organism, protist, blood cells, and most of the microbes which are around few microns in diameter can be imaged in bright field microscopy, provided we stain them.
Sir, how can we image refractile objects using bright field microscopy?
Yeah, bright field microscopy also have some limitation, and one of the limitation is that if they are refractile objects, because they will appear more brighter, it's very difficult to image. For that, we use something what we call the dark field microscope. So how does a dark field microscope vary from a bright field? In dark field microscopy, just after the light source, the condenser is so adjusted along with some field stops so that bulk of the light does not enter the objective. Only light which is diffracted by the object enters the objective, due to which the specimen plane actually appears dark and only refractions from those appears bright. Hence, refractile objects is best viewed by using dark field microscopy. Now, coming to the end of this session, let me summarize what we have discussed. We have discussed about the history of microscopes. We have discussed about different concepts which is important in understanding how a microscope function or how a lens function, and then we have just introduced you to different types of microscope, giving you an overview about bright field and dark field microscopy. Thank you very much.